permission. Okay.
Yes, sir, I start.
Okay, good. So what I was talking about, actually in our last 7 weeks, I would say, we have discussed about our time domain representation of signals and systems. From today ahead, we will be discussing about transfer domain of representation of LTI system. Transfer domain involves transformation mathematics. We will start from Fourier transform and Fourier series. Then we will introduce Laplace transform, how that can be used to represent or analyze our LTI system. As you know, that Fourier series is actually a mathematical technique by which you can transfer your time domain quantities to frequency domain. So in this mathematical technique, we usually we start from our time domain signal. Then this time domain signal is transferred into frequency domain by using this Fourier mathematics. Now you see that we have many types.
Excuse me, sir.
Yes.
In Fourier series, we only break down the frequencies into fundamental components, right?
Let me finish my lecture first, then you will understand what is the thing that is there in Fourier series. Okay, just let me introduce the thing first. The thing is that if we have because your Fourier mathematics is not only Fourier series, some other things are also involved there. So if we have our time domain signals, then what you need to do? First thing is that you have to extract what is the frequency component present in our signal. That frequency component in our signal cannot be estimated so easily in the time domain, because we have our classes of signal. Those signals can be classified as say in terms of the nature in which they are varying with time. We can classify a class as periodic type signal, and the rest class is the second class is say your aperiodic type. Aperiodic means not periodic. If we have a periodic signal, now a periodic signals have different mathematical representation. Cosine or sine omega t or sine t cosine t are the ideal examples of periodic signal, but those signals will have a single frequency. But if we have our signal that are periodic but not exactly equal to sinusoidal, then what we need to do, we can approximate that periodic signal with the help of the basis functions, something like that, sine and cosine omega t, or even by exponential functions, complex exponential functions. So this technique is actually representing a periodic signal by using some eigenfunctions like cosine omega t, sine omega t, or in general exponential periodic functions like e to the power j omega t, is a technique that we sometimes referred as Fourier series, because it will be coming in the form of a converging series. That means the periodic function can be approximated by a series of sine and cosine functions, or equivalently by a series of exponential functions. So those are the functions that is present in a pool. For example, we will be picking up the functions from the pool to represent a periodic signal, so that the error between the original signal and the represented signal will be minimum. This is what the logic of Fourier representation. This mathematics is Fourier series. We have another class of signals where no periodicity is there. Those signals are aperiodic type, but although they are aperiodic, some frequency component will be there inside the signal. In order to extract this frequency, we use another version of Fourier mathematics. This is called Fourier transform. Can you tell me what is the difference between Fourier transform and Fourier series? What have you learned in your mathematics?
Sir, we learned only Fourier series.
No Fourier transform?
No, sir.
But I have seen in your syllabus that Fourier transforms are also there.
No, sir, we have not learned.
Not when you are dealing with communications? No?
No, sir.
Then how did you learn your communication if you do not know a bit about Fourier transform? Because whenever we are communicating something, frequency is the one important issue of your input signal, as well as you have to design your system in such a way so that the system can process your signal.
Sir, we are told that we will learn that Fourier transform in third year.
In your third year?
Yes, sir. We had our communication course in second year. So during that time, the teacher said that we'll learn Fourier transform and all those transfer techniques in third year.
So in your third year, did you learn it?
Sir, we are learning this now.
In your mathematics?
No, sir, in signal and system course.
In signal and system course is not a mathematics course, because your mathematics course are already over. In those mathematics course, you have your Laplace transform, you had your differential equation, you had your Fourier transform and Fourier series there.
So we covered Laplace and Fourier series, but not Fourier transform in math.
Did you compare your syllabus with what your teacher delivered to your classroom? Have you seen your syllabus, that what is there in your mathematics syllabus? So
Yes,
this,
sir.
but I think transform technique is there.
Yes, sir, but
So this is what the problem with you, okay? Your teacher is giving you a course plan at the beginning, but you never compare your course plan with the progress or in course of time to what extent it has been covered or not. This course is actually an applied type course where we will set a relationship between engineering and mathematics. If you want to turn to mathematics to that extent, then the rest important part will be left unfinished. For this reason, actually, although we are giving some introduction, but we are expecting that you have a firm what we call background on those mathematics from your mathematics course. Okay, anyway, we will be discussing the thing there. But the thing is that if we have a signal that is aperiodic type, those
excuse me, sir, are you sharing your screen?
I will share your screen, okay? Before introducing something, then I will share the screen.
Okay, sir.
So the thing is that if we have our aperiodic signal where periodicity is not there, but still we can extract the frequency content of the signal by using a Fourier mathematics. That is what the extension of your Fourier series. In general, a Fourier series will contain some discrete frequencies. Those frequencies, as you were telling earlier, that we have a fundamental frequency of periodic signal that is determined by the frequency of lowest frequency of your periodic signal, and we will have our signal with frequencies that are integer multiple of fundamental frequencies. Those signals are called harmonics of your fundamental. And how many harmonics will be there? Theoretically infinity, but practically we do not need infinite numbers of harmonics to represent a signal. We have some mathematical technique that will tell you that your Fourier series is a converging series. As a result, it will contain some discrete frequencies. Frequencies of your individual components will be known to you, but you will not know the amplitude of your individual component. The central problem of Fourier series is to determine the amplitude of the individual harmonic component. But Fourier transform is a bit different, where we will have a continuous frequency present there. We will be discussing this thing from this point ahead. Before going to that, let us start with the thing formally. Okay, it is from chapter 3 of your book, and I have prepared this thing from there. Okay. So how to represent a signal, because the thing is that we have to start our thing from the signal, then we will transfer the signal or extract the frequency content of the signal. Then this signal will be fed to the LTI system. Then we will investigate the nature of the behavior of the LTI system. Many of the things probably have already been there with you from your control engineering. Okay, the logic is very simple. Okay, in order to develop the mathematical representation, how we will be dealing with Fourier mathematics in our signals and system, we will start from this very simple something. Okay, we will be dealing with discrete time signal first, then go to continuous time signal. Okay, in accordance with the presentation of your book.
Yes, sir.
Okay, the logic is what? Logic is we have to select a basis function so that your signal can be represented with the help of this basis function. In our Fourier mathematics, we assume that our signal can be represented by a basis function, something like this. This is sometimes called everlasting exponentials. Okay, this is your discrete signal. If we have a discrete signal xn, we are considering that xn can be represented by a everlasting exponential signal of this type, e to the power j capital omega n. And we know that capital omega is the periodicity or fundamental frequency of your discrete time signal, that you know that it is equal to what? Twice pi divided by n. Now, if your frequency is known to you, and that frequency can be continuous or discrete depending on the type of xn, but for development of the general technique, we will be assuming that we have a signal xn that has a frequency omega, and your signal is expressed by an everlasting sinusoid. Okay, so that your signal is what do you call it, as it is something like this. It can be periodic or it can be aperiodic depending on the type of your signal. Now, if our assumption is something like this, why we are assuming this? We are assuming this because in our Fourier transform mathematics, we will be expressing our discrete time or our continuous time signal in the form of sinusoids, or equivalently in the form of exponentials. As you know that our exponential functions are, say, if it is e to the power, say, j omega n, that is equal to what? It is equal to cos omega n plus j sin omega n. So these two quantities are equivalently can be used to represent our Fourier system. Okay, either we can use cosine, we can use sine, we can use our complex function e to the power j omega n. But representing with e to the power j omega n is more general. Okay, so let us start with this thing, that our signal has this type of time behavior. So if we assume this thing, then we know that from our convolution sum, that your convolution sum, say if the impulse response of your function is known to you, then for any arbitrary input xn, the output yn can be represented by this convolution sum. You know this thing, isn't it?
Yes, sir.
Now we replace our x by this function. If we replace our x by this function, then you see that x n minus k would be equal to e to the power j omega n minus k. Then we, after just split e to the power j n minus k into two terms, and your sum is over k. So we can take e to the power j omega n out of the summation. Then we will have a sum something like this. That sum will contain hk e to the power j omega k. Okay. Then this sum is represented by a function h e to the power j omega. Okay. In this book, actually it is represented by in this way, that h, a function of e to the power j omega, it is a function of frequency. In many other books, it is also written as, in discrete case, it is written in this way, h omega, or in some cases we write it h j omega. Okay, for continuous time case. So all are the similar type of representation. So after having this thing represented in this way, you can see, for example, that the relationship between input and output will take this form. Yn is equal to h e to the power j omega, the function of e to the power j omega and e to the power j omega n. You see that your input, consider the time variation of your input and output are not the same.
Yes, sir.
You see that this form of time variation to the input, because this form of time variation to the input is reflected to the output, and they are related by a term. That term is h e to the power j omega, and this can be expressed by a sum, something like this. And this function h omega is actually coming from the impulse response, and it is the function of frequency, and in general it is a complex function. It doesn't contain any time. This quantity is called, in general we call it transfer function. You learned it in your what?
Control system.
It is transfer function, okay, or equivalently called frequency response. Frequency response, okay, frequency response of your system. And it is a complex function. In general it will have a magnitude spectrum as well as a phase spectrum, okay. It will have a magnitude and an angle, and this representation is actually very general. So for any frequency omega, this equation will hold. Now the case is that if we want to apply this thing to our system, then what will happen? We did not tell anything about the time nature or variation of xn. Your xn can be periodic or xn can be aperiodic.
Yes,
if your xn is aperiodic type, then your omega will be continuous, and if your xn is periodic type, that you know that periodic signal will contain frequencies that are integer multiple of what frequency? Fundamental. So say if we consider that we have a signal with omega 0 fundamental, then we can have our frequencies there in your signal that is the integer multiple of omega 0, isn't it?
Yes, sir.
Your k cannot be 1.5 or 1.2 or something like this. Your k can be 1, 2, 3, 4, 5. In general, in some cases the odd values of k will exist. In other cases the even values of k will exist. But in general both even and odd values of k will exist. So your omega, the frequency of your signal, will be discrete one. That means the frequency of your signal will be the integer multiple of the fundamental frequency if your signal is periodic. But if your signal is not periodic, then theoretically the value of omega will be continuous. It can range from minus infinity to infinity. Now the thing is that why it is coming to minus infinity? Because there is no any physical significance of minus infinity of a frequency or minus frequency. But you will see that probably I have discussed a bit about it in your earlier classes, that if we have a signal, consider that we have a signal xn, although we have written this signal in this way in general, but if your signal is something like this, then what will happen? Your signal is actually become complex, isn't it?
Yes, sir.
But if you have a real signal that you want to prepare from a complex signal with frequencies, then what will happen? You will need, for example, two frequencies, one in minus n, the another is plus n. The reason is that you know that if we have a say cos omega, your cos omega equal to what? Half into e to the power minus j omega plus e to the power j omega.
J omega.
So now the thing is that this if we do not have, for example, minus omega with us, can we generate mathematically the real signal by using sinusoid? or exponential form?
Yes, sir.
Impossible. So for this reason, you will see that, and I hope that you learned it in your Fourier series. When we will be talking about Fourier series, we have two different forms of Fourier series. One is called trigonometric form, where your signal will be expressed in terms of cosine and sine omega t. But by using Euler identity, you can easily transfer this trigonometric form into another general form. We call it exponential form. If we transfer a signal into exponential form, then what will happen? If both your k value should be negative and positive, otherwise your signal cannot be made real. Okay, we will
Yes, sir.
discuss the thing later when we will be coming with it. So this is what our Fourier mathematics. By using Fourier series, if we can express our signal by using sinusoid, then we can find the output of your signal, and you see that for your linear time invariant system, your output will also be sinusoidal with same frequencies. And we can investigate the nature of the LTI system by using a quantity called transfer function. It is coming from what your impulse response of your system. And you will see that this equation that we have written here as a sum is actually the Fourier transform of a discrete time impulse response. We will discuss the thing later. Okay, so this is how your general way of proceeding with your Fourier mathematics. Now let us extend this thing for the continuous time case, and hopefully you will see that for continuous time case the thing that you have learned in your mathematics will be they are exactly what you have seen. Now you see that for the CT case, you know that the output of your system is the if the impulse response of your system is known to you, then output of your system yt is equal to the convolution integral of your impulse response and the input, isn't it?
Yes, sir.
So actually this equation was minus infinity to infinity h tau into xt minus tau d tau. We are assuming that in our case our signal xt is equal to e to the power j omega t, like our discrete time case. Then you can replace your x by using these exponential functions. Then you see that you can separate e to the power j omega t term. Then you have this integral with you. That integral is represented by h j omega, and you see that we are obtaining a similar type of equation that relates your input with output, and you see that h j omega is actually what is the thing? It is equal to your h j omega is equal to what? It is not that integral minus infinity to infinity h tau e to the power minus j omega tau d tau.
Yes,
Is
sir.
it?
Yes, sir.
Have you seen this integral earlier in your mathematics? No.
No, sir.
This is what actually the Fourier transform equation. Okay.
Yes, sir. Yes, sir.
So this quantity h j omega is nothing but Fourier transform of your impulse function, and it is called transfer function or frequency response. It is in general it is complex, and it will have a magnitude as well as phase angle. Okay.
Yes, sir.
The thing is not very complicated to be understood. It is a simple mathematical optical procedure, but many of the things related to is already known to you. But the problem is what? Only few of you are engaged in learning, but most of you are not engaged in learning. Okay. For this reason, still at your third year, you cannot identify what is your current source, what is your voltage source. You cannot write your Kirchhoff's equation, both your Kirchhoff's current law and voltage law correctly. So I don't know when you will learn those things and apply that thing. Okay. Yeah, almost 80% of the student has this confusion.
Yes, sir.
So this is not new thing. We have learned this thing earlier. And another tendency of coping with you, okay, I have detected few, I will discuss the thing later. Okay, so this is your, okay. Now probably we have heard about this thing earlier, isn't it, when we discussed about impulse response of an RC circuit in your chapter 2.
Yes, sir.
That if we have an RC circuit, it is simple representation of a LTI system. Then we know that if we take output across the capacitor, then the impulse response can be determined in this way that we have learned earlier. Now the thing is that if your impulse response is with us, then we can assume that if we apply our xt, that xt has a form equal to e to the power j omega t, then we will obtain an input-output relationship that is equal to h j omega, the transfer function. Now your transfer function can be determined if we want to use this integral. Then what you need to do, you need to know your ht, otherwise you cannot do that. So this example actually illustrates that how if your ht is known to us, then how can we find h j omega. It is very simple, that your ht is there, you just simply integrate this equation, then you replace your ht by using this ht. Your ht is equal to k, and a dummy variable tau is there, so you know this thing. And this is your ht, your variable is t is replaced by tau, and this is e to the power j omega tau d tau. Okay, then you can express this integrand into this form, and your u tau is a unit step function with value equal to 1 for tau equal to 0 ahead. So if we integrate from minus infinity to infinity in general, but we do not need to integrate from minus infinity to infinity, because your impulse response is from time t equal to 0 to infinity. So we can integrate from 0 to infinity, anybody can integrate it, and you will find that after evaluating this integral we have this transfer function. Okay, now compare this transfer function with the circuit theory. Is it not, for example, the ratio? Okay, if we transfer this network into frequency domain from your what do you call, you learned from in your first year that if we have an RC circuit, okay, your R can be there in the frequency same, but the impedance of your C can be represented by j omega c, isn't it?
Yes, sir.
Then if we have an input there, say converted into phasor form, say this is your x, and then your output is also converted to phasor form y. Then what is the relationship between x and y?
Sir, voltage division.
Voltage division. So your y divided by x would be equal to simply
1 by j omega c.
1 by j omega c divided by
R plus 1.
r plus 1 divided by j omega c, isn't it?
Yes, sir.
So is this equation is not equal to this one?
Yes, sir.
If we simply manipulate it, you will see that this equation is very similar to not similar, exactly equal to this equation.
Yes, sir.
So the thing is, actually we are gradually going to the same location. When we deal with alternating current, you know, alternating current is a periodic function, isn't it? And we assumed our alternating current as sinusoidal. As a result, what is happening there? We are actually using the same logic there in the alternating circuit. And we assume that if we have our input sinusoidal, then our output will also be sinusoidal, and accordingly we can process with representing our circuit elements, and we obtain the input-output relationship in a form that is very similar to what we obtain now. So in this way, the transfer function of your signal can be determined. By examining the nature of your transfer function, you can easily identify what will be the nature of your output. You see that your output is actually proportional to the transfer function. So if we know how your transfer function is changing with frequency, then you can easily understand that in which frequency range your system will be operating properly. And if it is not operating properly, then we have to change the design of our system. Okay, for this reason, the investigation of a transfer function is very important in designing an LTI system. Another issue is that your transfer function depends on the location of your input and output. If we change the location, then accordingly the transfer function will also be determined. Now for this particular problem, it is discussed there, although this is a very simple problem, you learned it in your second year or first year, I don't know. Actually, this is the transfer function of a simple low pass filter. You see that at very high frequency, okay, what is the nature of this impedance? 1 by omega c. That you see that for that DC case, it is infinity. Infinity means in the steady state, your capacitor will be behaving like an open circuit.
Yes, sir.
And as we are increasing the frequency, the impedance of your capacitor is decreasing. If the impedance of your capacitor is decreasing, then what will happen? The output will also decrease.
Yes,
And
sir.
theoretically, at very high frequency, output would be equal to 0. So your capacitor will be behaving like a short circuit.
Yes, sir.
So if we want to proceed in this way, then you can easily examine the nature of your output by examining the magnitude of H and a phase angle of H. H will have a phase angle, say phi H. That phi H we can easily determine from this complex function. Now, if we examine in what ways your H is changing with frequency, that will tell you that in which frequency range your circuit will be operating properly. Okay. So what is the nature of your H omega magnitude? Is it not inversely proportional to your omega?
Yes, sir.
It will have a value equal to 1 at omega equal to what? It will have a value equal to 1 at omega equal to 0. Okay, then if we change omega from minus infinity to infinity, you will see that that value will have a peak at omega equal to 0 and gradually going down, decreasing, and in both ends it will be equal to 0, isn't it?
Yes, sir.
And it is very similar to what a resonance curve or something like this. Although resonance will not occur here in the first order circuit, but still the shape of the curve will be looking there. Is it not that?
Yes, sir.
Okay, I was disconnected. Can you hear me now?
Yes, sir. You can hear you now, sir.
Because it was frequently getting disconnected. Okay. Can you see this figure?
Yes, sir.
Okay, that's it. So a few things that I will not discuss to that detail here because I am assuming that those things are with you. Okay, can you remember that this thing, 3 dB point or half power point?
Yes, sir.
What is it actually?
Sir, cut off.
Frequency.
It is not the cutoff always, okay? 3 dB point is the point where your power of your circuit is going to half. So at the half power point, you know that your dB is defined in what ways? Your dB is defined as 10 logarithm of 10, say power ratio P1, P2 by P1. If your P1, for example, and P2 is half, this ratio is half, logarithm 10 of half, that is equal to what?
Sir, 1 by root.
Log 0.5 equal to what? 1 by root 1 by root হলো এটা 5. Is it not equal to say -3?
Yes, sir.
Yes, sir.
So this is your -3. That means if your power is going down, if your power is, say, your initial power is 1 and your final power is half, then what will happen? This ratio become half. And if you want to express it into dB, then it will be equal to -3 dB in terms of power. If it is -3 dB in terms of power, so you see that the H omega that we are having, okay, this is very intuitive explanation. The magnitude of H omega we are having, is it related to power or your voltage or current ratio?
Sir, power.
Is it power? How can you say that it is power? Because we are obtaining this thing by using this ratio y divided by x. Why is it what? Is it power?
No, sir.
Are not they voltage?
Yes, sir.
Because this H omega transfer function is it has no unit. It is a ratio of similar quantities. It can be the ratio of power voltage, or it can be the ratio of power, current. It is not power. If we want to convert it into power, what do you need to do? We have to square it.
Yes, sir.
As a result, what happened? If, for example, we can express this ratio into power or voltage, 10 log 10 into, say, P2 by P1. Then if we want to express it into voltage or current, then what will happen? It will be equal to 20 log 10, either voltage V2 by V1 or 20 log 10 I2 by I1, isn't it?
Yes, sir.
So then what will happen? A 3 dB point in voltage and power will be equal to what? Will be equal to, if your power is going half, then your voltage and current will be going where?
-6.
It is simply equal to square 1 by square root of 2 times. Because you know that a square of your voltage or a square of your current is related to power. Then if your power is half, then your voltage and current will be equal to what?
Square root.
1 divided by square root of 2.
Yes, sir.
So this point is actually 0.707. And in terms of H, if we plot, for example, H omega square, then this point will be equal to half. So the half power point is defined where your voltage and current ratios are going to 1 by square root of 2 times lower, or your power is going to half. They are equivalent. So in this way, you can easily see that someone was telling that it is cutoff frequency. Actually, theoretically, we cannot determine exactly the cutoff frequency of our RC circuit. The reason is that the curve is something like this. But the nature is something like this. If we have a low pass filter, for example, then if this is your frequency omega, the characteristic of a low pass filter transfer function will be something like this. This is your omega C, the cutoff frequency. Within this frequency range, you have a constant gain, but beyond this frequency range, we don't have any gain. But practically, you will not have any filter of this type. What you need to do? We have to design a filter. That filter can have a transfer function something like this. Okay, it can be something like this, or even it can be something like this, what you have seen in the case of your RC circuit.
Yes,
So
sir.
in order to define this cutoff frequency, because you know that this cutoff frequency is cannot be determined because your curve is gradually going down. So someone can define your cutoff frequency here, other can define there. For this reason, we use some standard of defining the cutoff frequency, but general standard is 3 dB point. That means you have to consider your output usable to you if your output is gradually going to half of its magnitude. Okay, if your power is falling beyond that, we will not consider that output as a reasonable output. But this is a very restrictive definition of cutoff frequency. We have some other standards also. Now, I don't know whether this has been with you in designing your amplifier or not. So in designing amplifier or filter, we have many standards need to follow. For this reason, many specifications are there in designing the filter. Not only the cutoff frequency, you have to define your transition frequencies, you have to define what is the maximum allowable gain in the stop band or the minimum allowable gain in the pass band. All are the specifications of designing a filter. So if we, so the most generalized definition of obtaining the cutoff frequency is this one, that if power is going to half, then beyond that frequency, we will not consider the output as reasonable. So that frequency can be considered as your cutoff frequency or half power point frequency in terms of power. But if it is in terms of voltage and current, it is the point where your voltage amplitude or current amplitude is going down to 70.7% of your maximum value. Now, this is your magnitude spectrum. If we want to plot the phase, then by changing your frequency, you can easily plot your phase spectrum will be something like this. In your 3 dB point, you see that your phase difference between the input and output will be equal to pi divided by 4. And this is a simple circuit theory. Now, let's generalize this thing. If you want to generalize it, you see that this is a very intuitive vertical approach of determining the technique of Fourier mathematics, that how this can be applied to LTI system if impulse response is known to us. But if your system is LTI, otherwise, if your system is not LTI, then it is very difficult to apply this thing. But we are expecting that our all real systems can be approximated fairly accurately by LTI system. Now, if we have our signal, then, this figure, the lower one, is drawn, for example, for your continuous time case, but it is also same for your discrete time case. This figure will tell you the total approach for Fourier mathematics applied to LTI. Now, our first approach, first thing is what? We have to prepare our input. That means if your input is given to you, that input can be continuous time or it can be your discrete time, xn. The next thing is what? That xn should be, or xt should be expressed as a sum of our exponential functions, with known frequencies omega k. This is actually applicable for Fourier series in general, The reason is that we know that if we have a periodic function xt, that periodic function xt can be expressed as what you have learned in your mathematics, that it can be expressed as a constant term, say 0/2 plus some, say k equal to say 1 to infinity ak into cosine omega 0 kt plus bk into sine omega 0 kt. Isn't it?
Yes, sir.
Okay. Now, this equation is actually containing sine and cosine, Can we express this equation by using exponential, by using Euler identity?
Yes, sir.
Then that expression would be equal to what then? This expression would be equal to sum k equal to say minus infinity to infinity, a constant ck into e to the power j omega 0 kt. This is the equivalent representation, By using Euler identity, you can find your ck. And why we, in this equation, your k is ranging from 0. 0 would be equal to the average value. Then we have our k equal to 1 to infinity. But when we are expressing them in exponential form, you know that your xt is a real signal. And in order to express our sine and cosine omega 2 to exponential, you need your minus frequency. So your case should be from minus infinity to infinity, otherwise your xt cannot be generated. And that tells us that in our trigonometric form, your AK, BK, and A0 are all real. But in your exponential form, your CK will not be real. Your CK will be complex. But this complex has a nature, okay? It will be appearing as complex conjugate. The reason is that if we have a frequency omega and we are, for example, plotting our CK, then if for a certain frequency, say k equal to 1, we have an amplitude there. At k equal to minus 1, we must have another amplitude there. Otherwise, these two cannot be added together to find your real signal. In this case, what will happen? The amplitude Ck, if they are not real, then you C minus K should be equal to Ck conjugate, isn't it?
Yes, sir.
If they are not conjugate, then we cannot get the real signal. Okay, so because conjugate of two complex numbers added together, then we will get
Real number.
Okay, so that you need to consider that. Okay, this is very important thing to be considered. Okay, that if we express our periodic signal into which form? Trigonometric form, then your constants will be real and your signal is also real. And if we express it into exponential form, the Fourier constant will be complex, and your K Fourier harmonic should be extended from K minus value to plus value. And another thing is that your Fourier constant will be appearing as what? Complex conjugate form. Okay, so with this assumption that we are expressing our signal into, now the question is what? Another important question is there that we need to know. Okay, do we need to address? Okay, that question is what? Theoretically, our sum is from k equal to minus infinity to infinity, or from say k equal to say 1 to infinity for real case. But theoretically, if we want to design a system, can we go to infinity?
No, sir.
Then what we will do? We will do that, we will truncate this series into a finite number of terms.
Yes, sir.
That can only be possible if the higher values of omega, if the amplitude of the corresponding harmonics is very, very small, then we can truncate this series into a finite numbers of terms, and that will help us to model our system in practice. But theoretically, the thing is up to infinity. For this reason, for general purpose, here it is written that if we have a signal, this is also a very intuitive type explanation. We will be doing more detail precisely when we will be dealing with our system. If we can express our xt or xn into a sum of exponential functions, then you can use your superposition theorem there just to find the output. For example, say for each value of k, actually how many signals are there in xt? We have our k equal to 1 to m. That means a minus 1 numbers of exponential terms are there in your input. Are not they?
Yes, sir.
So that means you are splitting your input as like your convolution sum, okay, where we split our input into many components. So your x1 can be thought as many inputs, say x1t plus x2t plus x3t, something like this, okay, up to this sum. Then you see that in this case, if we are dealing with periodic x, then this quantity omega k will be known to us, because this frequency omega k is actually k times omega 0. If your omega 0, the fundamental frequency will be known to you. You know that omega 0 can be determined by continuous time signal, by t0, the fundamental period of your signal. And that will be given to your original signal. So omega 0 will be known to us. If your omega 0 is known to us, then all other frequencies will be the integer multiple of omega 0. So that omega k frequency will be known to us. The
Yes, sir.
only unknown thing will be ak. Okay, the ak is the amplitude of our harmonic components. That we know how to determine the Fourier constant. This is actually Fourier constant. So this is the thing that we usually do in Fourier series. We determine the Fourier constant ak or bk, or equivalently for exponential form ck. So once this is known to us, we can express our xt into a sum of exponential functions, that each of your exponential functions for a particular value of k can be thought as an input. So that input will give you an output. Similarly, if we sum all this output together, you will get the total output, and that total output will be something like this. Okay, for k equal to 1, we have a signal, say ak a1 e to the power j omega 1t, that will give you an output equal to h j omega, because h is your transfer function. We learned it in our earlier slide, that your h, if your h is known to us, then for that particular frequency omega k, we can find the value of h, multiply that value of h with ak, and you signal e to the power j omega kt, that will give you the output of that particular signal. And if we sum all the contribution up, then you will get your output. So in this way, we can calculate the output of an LTI system if your input is known to us. Okay, I will be illustrating this thing by using this example, that how can we calculate this thing. Okay, just I will be leaving something for you to be explored. But before going to that, let me examine whether our next slide, no, not next, then I will share your whiteboard to illustrate the thing. Okay, now let us start with this thing. That we have, for example, this RC circuit. Our output is YT, our input is XT, this is your R, this is your C. We know the H of your circuit, and corresponding H omega is also known to us. We have found that H omega for continuous case, your H omega equal to 1 divided by RC divided by j omega plus 1 divided by RC. Is it okay?
Yes, sir.
Okay, for simplicity, you can consider that we have a circuit with RC equal to 1 second. Okay, time constant equal to 1.
Yes, sir.
If we have time constant equal to 1, then it is further simplified as H omega equal to 1 divided by 1 plus j omega. Is it okay?
Yes, sir.
Fine. In your Laplace transform, it is 1 divided by 1 plus s. Okay, it is a simple transfer function of a low pass filter. Now, if we apply, for example, our x, say our xt equal to, say this, your xt equal to something like this, a square wave. Even you can perform this in your laboratory, although your laboratory is not accessible. And we applied this pulse when we use our oscilloscope to calibrate our oscilloscope. Have you ever calibrated your oscilloscope?
Yes, sir.
How we calibrate it?
Sir, horizontally and vertically by turning the knobs.
This is not calibration. Okay. So this is what the thing. Consider that we are applying a signal, a square wave of this form with amplitude equal to ranging from A to minus A, and your time period is 2 seconds. Okay. Is it not a simple periodic wave?
Yes, sir.
Okay. If it is periodic, what is the period?
2 seconds.
Period is 2 seconds. That means that period is actually it is a fundamental period. Okay, why we are calling it fundamental? Actually, this waveform, if someone will tell you that what is the frequency of that waveform, and what is your answer?
1 by 2.
1 by 2. Is that is your answer is correct?
No, sir. The fundamental frequency is 1 by 2.
Exactly, that is good. The fundamental frequency is 1 by 2, but or half hertz, but it is not the exact frequency because, but if your wave is, for example, purely sinusoidal, say your wave is something like this, sinusoidal, then what is the frequency? With same nature,
0.5.
it is 0.5, but this frequency is the only frequency that your signal contains. No other frequencies are there, okay? Because sinusoidal component cannot have different frequencies. If we have a fixed frequency, they are already present, okay? Now, because the
Yes,
reason
sir.
is that actually Fourier series, when we express Fourier series, I will be telling you to you how Fourier series can be thought as a device actually, or a filter to extract the frequency component of a signal. In one of my earlier classes, probably I talked about it. And you see, in our laboratory, in the last year, or probably at one point, I have tried to procure few equipments from your laboratory where you can experiment in Fourier series. Have you seen this equipment in your laboratory?
No, sir.
No. Okay, we have a simple machine there by which you can analyze your Fourier series. Even nowadays, if you have an oscilloscope, that oscilloscope can also generate your Fourier harmonic, that you can easily identify what Fourier components are present in your system. It is very simple, okay? For example, if you want to learn how many frequencies are there in your signal, what you can do, say you can give input. If you can give, for example, xt as an input to a system, say this is your system, that is a tunable filter, say it frequency can be tuned, and we have our output yt. Then what will happen? If your frequency, for example, of your system is tuned to f0, then what will happen? You will get the fundamental sinusoidal wave, isn't it?
Yes, sir.
Now, if your frequency is tuned to say 2f0, then if 2f0 frequency exists in your system, you will get an output sinusoidal with lesser amplitude. Similarly, you can go to tune to 3f0, then you again observe the output. If that harmonic is present in your signal, then you will have an output. In this way, you can tune your system to frequencies that are the integer multiple of your fundamental frequency, and you can easily examine that what frequency components are giving you the output, and that frequency components are the frequency component contained in your signal, okay? But this is what the logic. But if we want to calculate it mathematically, then how to do that? What you can do? You can do it in three different ways. In your earlier cases of cosinusoidal Fourier series, what have you done? You multiplied your signal xt with a function, say sine, say omega 0 into kt. Then you integrated it over the period from minus t by 2 to t by 2, t0 by 2, and dt, and you divided it by 2 divided by t0, okay? That will give you a constant, we called it, say bk, the Fourier constant bk. Can you remember it?
Yes, sir.
Okay. What is it actually? What does this operation mean? Is it not a filtering type operation, a comparison type operation? For example, if you xt and a sinusoidal, this function will be known to you, and this is only fundamental frequencies are known to you. Then if these two signals are very similar, then what you can do? Then you will get the integral. If they are dissimilar, you will not get the value of the integral. And that will tell you that at which frequencies you will get the maximum value of this integral. That will give the value of that k, a. And that is what the harmonic amplitude that is present in your system. It is very similar to the system that I described, okay? We are giving an input to a system with frequencies that are integer multiple of omega 0 k, and we are comparing whether an output is available or not. If that harmonic is present, you will get the output that is equivalent, equal to, you will get the value of this integral. And if you have no frequencies present there, that integral will be 0. So in this way, you can proceed with extracting what are the frequencies present in your system. So before coming to the next class, what you can do, you by using your earlier known technique, you express this equation into Fourier series, okay? Then you will see that in this equation, your sum of the Fourier component will be present and other will not be present, okay?
Yes,
If
sir.
your frequency component is not present, then what will happen? According to our previous calculation of LTI, say we have a frequency k omega 0 present. Then your H will not be continuous. H will also be discrete, okay? That means your H transfer function will be present in your discrete frequencies, okay? Not in all frequencies, isn't it?
Yes, sir.
If your fundamental present, then omega 0 present. If k equal to 1 present, then fundamental. If you k equal to say 3 present, then what will happen? You will get k equal to j omega 3. But between 1 and 3, you will not have any output. So as a result, what will happen? You can calculate your transfer function. That transfer function will also be discrete, and it is present in the discrete values of frequencies. So once your transfer function is available at that particular frequency, you multiply that transfer function with Fourier constant ak and multiply it with e to the power j omega 0 kt. That will give you the output of your RC circuit at that particular frequency. So if you can explore, you find the frequencies of your xt, then you calculate the corresponding values of h, then you calculate the output, and you can plot how your output will look like. We'll discuss further about it in the next class, inshallah. So you can stop your recording now. Okay, when our class will end?
So 10:30.
10:30.
Sir, we have 4 minutes left, sir.
Sorry? I cannot
Sir,
hear.
it will end at 10:30, sir.
Sorry?
Sir, it will end at 10:30.